In this lesson, we're going to explore the reactions of alpha-beta unsaturated carbonyls, introducing conjugate addition, and looking at conjugate versus direct attack of nucleophiles. Alpha-beta unsaturated carbonyls have an alkene directly attached to the carbonyl. We've seen that carbonyls are good electrophiles. Nucleophiles can attack the electrophilic carbon of the carbonyl, inducing acyl addition or acyl substitution depending on the type of carbonyl. Because of resonance, alpha-beta unsaturated carbonyls are electrophilic at both the carbonyl carbon and the beta carbon. The example here shows a simple alpha-beta unsaturated ketone. The various carbons of a carbonyl compound can be described based on their proximity to the carbonyl. Following the Greek alphabet, the carbons closest to the carbonyl are considered alpha carbons, then beta carbons, gamma carbons, etc. An alpha-beta unsaturated carbonyl will have a double bond between the alpha and the beta carbons. This creates conjugation and introduces resonance to the molecule. If we look at the second resonance structure, we can see that the beta carbon has a significant amount of electron deficiency, making it highly electrophilic. We typically think of alkenes as nucleophiles, but when alkenes are conjugated to carbonyls, they become electrophilic. The electrophilic character is spread out over both the carbonyl carbon and the beta carbon, meaning that nucleophiles can attack either position. Nucleophilic attack at the carbonyl carbon is considered direct attack or 1-2 attack. Direct attack results in the expected acyl addition or acyl substitution reaction that would have occurred without the alkene present. The example here shows an alpha-beta unsaturated ketone undergoing direct attack with a nucleophile. We know that ketones undergo acyl addition. The expected product would be the addition of the nucleophile to the carbonyl to give an alcohol. Nucleophilic attack at the beta carbon is considered conjugate attack, or 1-4 attack. The example here shows an alpha-beta unsaturated ketone undergoing conjugate attack with a nucleophile. The nucleophile is added across the alkene pi bond. The carbonyl remains unchanged. Nucleophilic attack at the beta carbon of an alpha-beta unsaturated carbonyl is called conjugate addition. It's important to note that the reaction will be an addition regardless of the type of carbonyl. In the example, we see that NUH has been added across the alkene pi bond. The mechanism for conjugate addition is straightforward and involves the formation of an enolate intermediate. In the first step, the nucleophile attacks the electrophilic beta carbon, breaking the carbon-carbon pi bond and resulting in the formation of a resonance-stabilized enolate anion. In the second step, the alpha carbon of the enolate is protonated to give the final product. Because alpha-beta unsaturated carbonyls are electrophilic at both the carbonyl carbon and the beta carbon, how can we predict whether a given reaction will occur via direct attack or conjugate attack? The site of reaction depends both on the type of carbonyl and the specific nucleophile used. We're going to break down carbonyl compounds into two subcategories: highly reactive carbonyls and less reactive carbonyls. The list of highly reactive carbonyls is quite short. Only acyl halides and acid anhydrides, the two most reactive types of carbonyls. These highly reactive carbonyl types almost always undergo direct attack, reacting at the carbonyl carbon. The list of less reactive carbonyls includes aldehydes, ketones, and the remaining acid derivatives: esters, amides, carboxylic acids, and nitriles. These less reactive carbonyls undergo direct attack with very strong nucleophiles and conjugate attack with weaker nucleophiles. For the purposes of determining conjugate versus direct attack, strong nucleophiles include Grignard reagents, organolithium reagents, and lithium aluminum hydride. The list of weaker nucleophiles includes pretty much anything else you can imagine: alcohols, water, alkoxides, hydroxide, amines, thiols, thiolates, cyanide, and Gilman reagents. It's easiest just to remember the three strong nucleophiles and consider everything else to be a weak nucleophile for these purposes. So let's take a look at a few examples that will demonstrate how to predict whether an alpha-beta unsaturated carbonyl will undergo direct or conjugate attack. The overall process is straightforward. First, we determine the reactivity of the carbonyl. Highly reactive alpha-beta unsaturated carbonyls, that is, acyl halides and anhydrides, almost always undergo direct attack. If the carbonyl is one of the less reactive types, then we need to consider the strength of the nucleophile. Strong nucleophiles like Grignard reagents, organolithiums, and lithium aluminum hydride will induce direct attack. All other weaker nucleophiles will give mostly conjugate attack. Let's look at the first example. We first consider the carbonyl type, in this case an acyl halide, which is one of the reactive types. Right away, we know this is going to do a direct attack. Because acyl halides are carboxylic acid derivatives, the reaction will be an acyl substitution. In this case, the nucleophile is methanol, transforming the acyl halide into a methyl ester. Let's take a look at the second example. Again, the first thing to do is to determine the reactivity of the carbonyl. Here, we see a ketone, which is one of the less reactive carbonyl types. This means we have to consider the strength of the nucleophile. In this reaction, the nucleophile is a Grignard reagent, one of the big three strong nucleophiles. The less reactive carbonyls undergo direct attack with strong nucleophiles. We know that ketones undergo acyl addition, so the reaction here will be the addition of the Grignard reagent across the carbonyl to give an alcohol. Let's try the next example. Here, we see an alpha-beta unsaturated aldehyde. Aldehydes fall into the less reactive carbonyl category, which means we need to consider the strength of the nucleophile, which in this case is cyanide. Cyanide is not one of the big three strong nucleophiles, and the less reactive carbonyls undergo conjugate addition with weaker nucleophiles. In this case, the reaction would be the conjugate addition of cyanide to the alkene. And be careful that you add the nucleophile to the beta carbon, not just the last carbon on the molecule. In this example, the reactant already had a methyl group attached to the beta carbon, which means that the product will have both a methyl and a cyanide group attached to the beta carbon. If we look at the last example, we see an alpha-beta unsaturated ester. Esters are not one of the two highly reactive carbonyl types, which means we again must consider the strength of the nucleophile. In this reaction, the nucleophile is a Gilman reagent, and Gilman reagents are not among the big three strong nucleophiles. Be careful not to overgeneralize the three strong nucleophiles. A Gilman reagent is an organometallic reagent, but it is not an organolithium reagent. Because the less reactive carbonyl types undergo conjugate addition with weaker nucleophiles, the reaction here will be the conjugate addition of a methyl group to the beta carbon of our reactant.